Okay, so next up is going to be an example that uses this last special case we had to think about, which is complex roots. Just to kind of get you thinking about where this is going to lead us. But the problem is going to be that we're solving a differential equation given by 4x squared y double prime plus 17y equal to 0. That's an x right there. All right, so this is a Cauchy-Euler type problem because it's got, it's a little different from the others we've seen so far. We always had all of the derivatives involved. But even though we're missing kind of a, it's not like 4x squared y double prime plus 3xy prime plus 17y, even though that thing in the middle is gone, as long as we're still following that rule that there's a squared on the second derivative and there's an x to the 0 or no x on the regular y, we're okay here. So this is Cauchy-Euler, and we can go ahead and solve it same way we've been practicing. So we're going to assume y equal to x to the m is a solution. Then we're going to have y prime equal to mx to the m minus 1, and y double prime m times m minus 1, x to the m minus 2. And so when we plug this into the ODE, we're going to get 0 is equal to 4x squared y double prime plus 17y, which is 4x squared y double prime right there. That's our m times m minus 1, x to the m minus 2, plus 17 times y. That's just our original x to the m. And when we combine those x terms together, we're going to get 4 times m minus 1 times x to the m. X to the m minus 2 times x squared is x to the m, plus 17 x to the m. And we can factor out that common x to the m. So we'll have 4m times m minus 1 plus 17 x to the m. So that means we need to solve 0 equal to 4m times m minus 1 plus 17 equal to 0. So we're going to have 0 is equal to 4m squared minus 4m plus 17. Let's see. I can't factor that. So that means that m would be given by the quadratic equation. So minus 4 plus or minus the square root of minus 4 squared minus 4 times 17 all over 2 times 4. So m is just positive 4 plus or minus the square root of 16 minus 16 times 17. I don't want to have to figure out what that is. All over 8. So that's going to be 4 plus or minus 4, 1 minus 17 over 8. Okay, I should do that, not skipping any steps in between. 16 times 1 minus 17 all over 8. I just factored out the common 16 in both those terms. So I'm going to have 4 plus or minus root negative 16 squared over 8. So that's just 4 plus or minus 16i over 8. So our complex roots are m equal to 4 over 8 would be a half, plus or minus 16 over 8 would be 2. So plus or minus 2i. I hope I didn't go through anything too quick when I was just making that arithmetic work. 16 times 1 minus 17 is 16 times minus 16. So minus 16 squared cancels out with the square root and creates an imaginary number. So those are our roots. And we always break our imaginary roots into their real and imaginary parts. So for us, that real part alpha is a half, and that imaginary part beta is 2. And the reason we break those apart is because those two different parts show up in our solution. The alpha is the part that looks like what your solution usually does, and then the beta is the part that goes inside of the cosine and sine functions. So our rule says the solutions should be x to the alpha cosine of beta natural log x and x to the alpha sine of beta natural log x. That's just the rule for complex numbers when we're solving this Cauchy-Euler type problem. So for us, that's going to be x to the 1/2 cosine of 2 natural log x and x to the 1/2 sine of 2 natural log x. And when I'm working through the problems like this, they probably don't seem very like complicated. You know, this function is complicated. It's not very pleasant to look at, but you know, plugging in the real part here, and the imaginary part here isn't that complicated. But there's a lot of opportunities to kind of just mess up with the form of this. You know, like it's really easy to write x to the alpha x on accident, or forget about your natural log inside the cosine because you don't use that in the constant coefficient. So just be careful. But we're not done with this problem yet. The general solution is just when we take the linear combination of those two things, y equals c1 x to the 1/2 cosine of 2 natural log x plus c2, I'm going to fix that cosine, c2 x to the 1/2 sine of 2 natural log x. And then from there, we've solved the problem. We have two unknown constants, which is what happens when we're solving second order equations. We would solve for those constants in an initial value problem. But that's what the solution looks like for these complex roots to our auxiliary equations for the Cauchy-Euler problem. So our final, probably final example is going to be a little bit more complicated. We're actually going to look at start to finish a non-homogeneous problem that uses this method. So if you need to, maybe take a break here because this last example will be long.